Chemical Engineering, Polymer Science 757, Polymer Rheology, Professor H. Winter. Our objective is to describe strains mathematically, and we were doing that by drawing material lines in the deforming medium. And those lines are changing their length, they are changing their relative angle, and if those lines are very long, they also curve in case of a large deformation. But we introduced the concept of locally homogeneous strain. So we're looking at infinitesimal small material lines. We look at those lines at two strains, or at two times, or two states. Excuse me. So a strain would transfer this material from its initial state, like here it's drawn as a lump of material with point P on a path line, and then as this piece of material is moved on in a flow, in a motion, point P is here, and the macroscopic shape has been changed due to the deformation. Now we are interested in small lines, material lines A, for instance, and line B, as they transform due to the strain. Line A prime will be transformed to line A due to the strain which we described with the strain tensor F. And I want to show you now that F is sufficient for describing the length change and angle change for those material lines. We say that the strain is defined by a deformation gradient, so F is given, and we choose two material lines, A and B. To come back to our previous picture, we are choosing A and B in the material at time t, and F is given to us, and we want to calculate A prime and B prime. Want to know whether we have all the information. The first information we would like to know is the length of A prime, and we are expressing the length of A prime in terms of A and F. Actually, the basic formula I didn't even write down on these papers. We are saying that vector A prime is equal to vector A times the deformation gradient F, and the same holds for vector B. If you could show this on the screen. So this is the transformation formula between the two states. So we are expressing A prime in terms of AF, and the magnitude of A prime then is given as A dot F dotted into itself. So it's times A dot F and the square root taken of that. Right? Now we interchange the order by using F transpose. So this would be then the square root of A dot F dot F transpose times A, taking the root of that. And you can see that a new group appears in that calculation, and this is called the Cauchy tensor C. But clearly, if we know F, we know F transpose, and we can calculate the length of vector A in the previous time or previous state t prime. Now how about an angle change? An angle change between t prime and t is described by the change of cosine theta. Cosine, here we're looking at the angle, cosine theta at the prime state and cosine theta then at time t. Now, the cosine theta is given by the scalar product of vector A with vector B, and it's multiplied with the magnitude of A and B. So if we express the theta in those two states with the scalar product A prime times B prime, and the magnitude divided by the magnitude of A prime and B prime, and we're scaling the whole thing with cosine theta, and then the ratio is appearing like this. We replace all terms in this equation by all prime terms, like A prime, we replace that with A, and B prime with B, and we express this whole fraction with A and B, and you can see that the old angle cosine theta prime is completely defined by this expression. Nothing new had to be introduced. If we know F, we can calculate the ratio between cosine theta prime and cosine theta. But again, look at this. We don't need F by itself. We need this product, which we call the Cauchy tensor C, and it's appearing in several places here. So what is this Cauchy tensor? You have to learn more about that. It's the Cauchy tensor will help simplifying our approach. Actually, it's easier to work with the Cauchy tensor, and you will see that. So because the Cauchy tensor contains less information than the deformation gradient. So C is defined as F dot F transpose. That's the definition of the Cauchy tensor. And as we saw, this tensor describes length changes between T prime and T, and it describes angle changes between T prime and T. And that's all we need for describing a deformation. So C is sufficient for quantifying a deformation. The tensor is symmetric, and that's occurring by definition. If you have any tensor, say tensor F in this case, and multiplied with its transpose, that product is a symmetric tensor. So C is a symmetric tensor. The components Cij are equal to Cji. You can interchange the components. Or in a matrix form, a symmetric tensor means that when you look at the diagonal, the upper half components in the upper half are equal to the components in the lower half. Now, very often we use the finger strain tensor instead of the Cauchy tensor, but it doesn't contain new information. It is just the inverse of C. So you can manipulate. You can actually define an infinite number of different strain tensors using the deformation gradient tensor as a starting point. F gives a complete description, it completely defines the deformation from T prime to T, and then you can define whatever strain tensor you would like from that. So, but we will stay with C and C to the minus 1 with the finger tensor, and that's completely sufficient. Let's look at this a little in little more detail. If I move this in the middle, I'm really interested in this formula. F, the deformation gradient tensor, can be decomposed into a orthogonal rotation tensor and a stretching part, stretching tensor U. Now you can do this with any tensor. You can decompose any tensor in those two components, in a rotation component and in a component which describes the asymmetry of that tensor. Now, the property of the orthogonal rotation tensor is given here. The inverse is equal to the transpose of that rotation tensor. That means if you multiply R into R transpose, you get equal to 1. You get a unit matrix. That's the property of a rotation tensor. Mathematically, you use rotation tensor to multiply maybe parts of an equation or another quantity, and then the effect is that you rotate everything by doing that. At the end of this class, I will show you an example of rotating a coordinate system. Now, when decomposing f into those two components and introducing this in our definition of the Cauchy tensor, f times f transpose, you see the groups coming up here. U R transpose are equal to, reversing in order, R transpose times U transpose. And in this product, you can, the order of taking the product is unimportant. You can choose that freely. So R times R transpose, we would take that first. That's equal to 1. And it will be, it doesn't affect the product, so that C can be expressed at just U times U transpose. And that's the result we are having here, down here. So it shows that the Cauchy tensor only captures the strain contribution. It doesn't capture the rotation which happens during the deformation. And that's quite important. Remember, we started out with the motion, the complete motion of a material element in a channel, for instance. And that motion consisted of a translation, of a rotation, and a strain. Now, by introducing the deformation gradient tensor, we eliminated translation, and we still had rotation and strain described in that situation. By going from the deformation gradient tensor now to the Cauchy tensor, we eliminate the rotation. And that's what I just showed you in this manipulation. So C, the Cauchy tensor, is a measure of the strain independent of rotation and translation. And that strain will be used in constitutive equation for the stress, because rotation translation would not affect the stress, except for some inertial terms, but we are talking about low Reynolds numbers. Yes?
On the rotation tensor, dot product with its transpose equal to 1.
Yes.
Why is it, or what makes it equal to 1, or if that's the case, why then is not the left tensor also equal to 1?
Yes. The question is about the manipulation I used here for the rotation tensor. Let's start out with the definition of R times R to the minus 1. Now, this for any tensor, if you multiply that with its inverse, you will get a unit matrix, which means that in every coordinate system, a simple matrix like this is used to describe the tensor. So that's the definition of the inverse. Now, the rotation tensor specifically has the property that its transpose is equal to the inverse. That's only true for the rotation tensor. So in our case, we could write now R dot R transpose and say that this is equal to the unit tensor. So the upper part here is a general property. That's the definition of the inverse. This property is specific for the rotation tensor.
That result to be orthogonal, or the orthogonality of the system?
It has to, yeah, it's orthogonal, and it's just rotating everything. If you would have a non-orthogonal, so you would have finite values here, and the whole property would not hold anymore. So the Cauchy tensor describes the strain, and it eliminated the translation and the rotation from the picture. Now let's look at the components of the Cauchy strain tensor in shear flow and in extensional flow. In the upper part, we just take, as calculated in the last class, the components of the deformation gradient in shear flow. This is the shear flow picture. Deformation gradient. multiplied with its transpose, and the multiplication of those two matrices goes something like this. If you want to calculate, say, this component, you take these and these here. And the first term is multiplied with the first term, added now to the product of this term times that term, plus this term multiplied with that term. And in summary, this is minus gamma. So that's how you calculate the Cauchy tensor in shear flow. And you can invert that, can perform the inversion. Either you perform the inversion with the finger strain tensor, and then you get the result automatically, or you take the Cauchy tensor and invert that matrix. So either one is possible. In extensional flow, we have an even simpler case. You take the, I put down the result immediately, the finger strain tensor and the Cauchy tensor here. F is given as L1 to the minus 1, L2 to the minus 2, L3 to the minus 2. And then when you multiply, when you produce this product, you get the square of those terms. And the same thing for the finger strain tensor. By the way, the name finger comes from a person about 100 years ago who straightened out those continuum mechanic terms. You know, there were always times in history where people struggled with the formulation of those tensors. So Finger used this type of tensor extensively. From all the strain tensors which we are free to use, we would pick the one which gives the most simple formulation of constitutive equations. That would be the criterion. Otherwise, we are completely free in choosing any type of strain tensor. It turns out that the finger strain tensor gives the most simple constitutive equations. There's a molecular theory for rubber, a first molecular model by Treloar and people in England. And the result of that molecular theory is a stress-strain relation, and the strain is the finger strain tensor. And later on, Large changed that for our elastic liquid, and again, he has a finger strain tensor in his constitutive equation and finds the most simple formulation with that. That's why I'm also adding the finger strain tensor when calculating the Cauchy tensor. It was more easy for me to calculate the Cauchy tensor because I could argue stretching of lines and changing of angles with you, and you could hopefully see that happening. So the inverse of the Cauchy tensor is the finger strain tensor. Now we worked quite hard to get here using a fairly simple picture, but it's quite involved. Let me use a different approach now, and this has been described by Lodge in his book in 1964. Very nice approach. We are going to look at deforming material. So the material goes from state T prime to state T. And we will look at three independent material lines in that deforming material to describe the strain. If we know three lines at both states, T and T prime, then we can calculate F and everything is defined. We are free to choose any material lines. So whatever is convenient, we can choose. But those lines have to be linearly independent. We cannot take one line and another line being just collinear but a little longer or so. They have to be in some angles. They have to be independent of each other. So Lodge now picked three lines which at time t are of unit length and at right angles. So at state t, our three material lines coincide with the coordinate system, delta 1, delta 2, delta 3. He's free to do that. At some other time before or afterwards, we're talking about memory effects, or we're talking about something happening before. At some earlier time, these lines have been longer or shorter and in some different angle and have been rotating and all of this. So the strain is not limited by introducing that concept. There's no loss in generality. And he derived now the following relation. He said if we look at the material lines here, that would be just a base of just having unit vectors in the three directions. So that's not very interesting. But if we take the material vector in the previous state, at the prime state, and multiply, say, E1 prime with E2 prime in a dot product, then we get the component C12. We get the components of the Cauchy tensor. Okay? Now, in this case, you just look at a deforming material. You draw your lines conveniently in that material, and immediately you get the components of the Cauchy tensor. Let's do that. I'm not going to derive this relation, but you can check that fairly easily. Also, it's about, I think, the second chapter in Rheology's book, pretty much in the beginning where he works with those systems. And I took a figure here from Rheology's book saying shear flow, which is characterized now by three lines. At time t, our three lines are of unit length and orthonormal of right angle, yeah, unit length. And if we would write the components now of those at time t, it would be just, this would be 1, 0, 0, and E2 would be 0, 1, 2, and E3 would be 0, 0, 1 as components in our coordinate system. Now, how about the components of the three vectors at a preceding time, t prime? E1 has the same length as before, and its components are given as 1, 0, 1. It's not changed. It's not affected by the shear flow. Let's jump to 3. The 3 material vector is also not affected by the shear flow. It's sitting there, has unit length. It's right angles with E1. So E3 at the prime state has the component 0, 0, 1. Now, how about the 2 coordinate? The 2 material vector at a previous time, this vector has a 1 contribution, has a 2 contribution going up, and it also has a 1 contribution going sideways. And we know that the size of this contribution here, that's equal to gamma, because gamma was the tangent of angle alpha, and if this is of unit length, then this length up here is equal to gamma. And gamma is equal to the integral of g prime of the g dot, excuse me, integral of gamma dot, the shear rate from t prime to t. So this is our shear, and the one component here is in negative direction, so we have minus gamma, a 2 component is 1, and a 3 component is 0. Okay? Now note that these 9 components here, when you look at them like they are exactly the components of the deformation gradient tensor and shear flow. That's what we calculated before. So if you go some pages back, you will see that this is basically F, which we calculated. And now if we produce the dot product, say E1 dotted into E1, we get C11, and that's equal to 1. Or if we dot E2 into E2, we would have gamma squared minus gamma times minus gamma is gamma squared, plus 1 times 1 is plus 1, plus 0. So on the diagonal, we have 1 plus gamma squared. And equivalently, you calculate all the other components, and you're done. That's quite elegant, isn't it? It's a very nice approach. What Rheology is doing here is he uses the material vectors as a coordinate system, as a material coordinate system which is deforming with the material. And he would say that the Cauchy tensor then is just the base, the base of a co-deforming coordinate system. The process is even simpler in extensional flow. Let's take, again, two states, a deformed state at t prime and a current state time t. By the way, I handed out a new sheet for that, for this specifically. So the state at time t is given by an orthonormal system again, and we would calculate the components of the Cauchy tensor by the product E1 into multiplied with E1. That gives us the stretching in the first, 1 over the stretching in the first direction. I should talk about the stretching. See, and it has a small length in one direction, and this length is increasing. So the ratio of the old length t prime to the new length at t is defined as the stretch. And we would do this in all three directions. This would be the stretch in one direction if you take E1 divided by E1 prime. So in terms of the three stretches, now we can define the components of the three material vectors, and with those we get directly the components of the Cauchy strain tensor. And that's it. Now you can invert that, and then you get the components of the finger strain tensor. Interesting now is to look at the invariance of those strain tensors. Every tensor has invariance. Those are scalar properties which are independent of the choice of coordinate system. Now, a symmetric tensor has three invariants, and they are defined conventionally as the following. The first invariant of the Cauchy tensor is equal to the trace, the sum of the terms on the diagonal of that tensor. For instance, for extensional flow, we would take the sum of one term, two term, and three term, and this would be the first invariant of the Cauchy tensor. The second invariant is defined somewhat more complicated. This definition comes out of the Cayley-Hamilton theorem, if somebody interested. So I don't want to go into details, but that's why this specific choice has been made. And the third invariant is given by the determinant of C, describing density changes of the material. With those three invariants, you can define an infinite number of scalar invariants. So another choice, which is quite common, is C double dot C, which is kind of a scalar product of the tensor. And I wrote it down here in terms of the invariants, first and second invariant of the strain tensor. Okay, so strain tensor is characterized by, by those invariants. And I want to use graphics now to discuss those three invariants with you. So far, I always used a cubical material element for describing the strain, but that's not necessary. We could use a sphere at time t, drawing, we could take our material and draw a spherical surface in this material, and then when deforming this material, the sphere would be transferred into an ellipse, at least if we go just from state 1 to state 2. If we have a subsequent flow, we might have all kinds of complicated states. But if only two states are involved, we can describe the deformation by using a spherical surface and an ellipsoid in space. And that's what I was doing here, describing the lump of material at two states. And let's take, again, state T, where we describe the material with a spherical surface, which that's equivalent to Lodge's approach using an orthonormal system at time t. And at some previous time, the sphere would be distorted, say it would be an ellipsoid, like this. The axis of this ellipsoid are the principal axis of the strain. That is, if you would pick a coordinate system in this, well, if you would pick a coordinate system with this rectangles in time t prime, then you still would get a transformation, I mean a material coordinate system. You still would have a transformation of that material coordinate system into an orthonormal system, because every coordinate system you choose here, every set will be transformed into the spherical system, into the sphere. Okay, so if you choose a coordinate system which is collinear with this axis, with that axis, and the third axis, that's the principal coordinate system of the strain tensor. And the point I'm heading to is now the stretching of material planes in that deformation from t prime to t, and the stretching of lines. Which material plane going through point P would be stretched the most? You can choose any material plane, and that plane will be stretched or will be compressed, will shrink when the material is transformed from state t prime to state t. Certainly, whatever surface you choose within that ellipsoid, that surface or that plane will be a circle in time t. So let's choose the smallest surface in state t prime, and that's given really by the ellipsoid given with the axis B and C. So the maximum stretching we would get between this area at time t and an area of that same material plane at time t prime is given as 1 over b times c. And similarly, we could say the lines which are stretched the most would be the small axis in the ellipsoid, so this is 1 over c. That gives us the maximum stretching, which occurs during that deformation. We could take now an average. Instead of looking just at one surface, we look at an average of all surfaces. And the average which I picked here was this. I just took the stretching of the three planes, the planes going through being normal to the three principal axes, and I took the stretches of those three planes and summed them up. Now, instead of using the stretch by itself, I took the squares to emphasize the large deformation. So it's really dominated by the stretch. What did we say is the plane which is stretched the most? The plane was BC, so it's really dominated by this term. That's probably the largest term because that's squared and those are smaller. But we can calculate now the average area increase, and it's squared. That's where the square comes in. And that's given here, then when you rearrange this at a squared plus b squared plus c squared divided by the product of a squared, b squared, c squared divided by 3. And we can express that in terms of invariance. The first invariant, taking the axis of the ellipsoid, is given as the sum of those three terms. That's in the principal coordinate system, like the three terms on the diagonal being summed up. And the second invariant is reduced to those terms, and the third invariant describing the volume is like this. So down here is the volume, and up here it's the volume squared. This invariant describes volume squared, and up here is the first invariant. So we could say the first invariant of the finger strain tensor describes the stretching of material planes. If that invariant is large for a flow which you are analyzing, then you can be sure that planes will increase their size. And it will be a good mixing flow, for instance. Now, for lines, we can go through a similar argument. We can take the stretching of the three principal axes. Again, we take the squares of the stretches, and this will be dominated by 1 over c squared. That's the biggest term. And we can rearrange that, and you will find that this is the second invariant divided by the volume term by the third invariant. This third invariant is equal to 1 if we have constant density. So we really could say that the second invariant of the Cauchy tensor describes the stretching of lines. So if that's large, then any line segments will be extended tremendously in that flow. So, but just looking at those invariants, you can quantify phenomena in the flow. Now, if you say look at molecular arguments, and let's say you represent molecular strands by lines, and then you argue, oh, in this flow you have a lot of stretching of lines, you can maybe argue that the molecule will be oriented. You order this molecule in that type of flow, like in a fiber spinning flow, for instance, you're stretching tremendously in one direction. Okay. Oh, and in that same framework now, most easily in largest framework where we look at the cube at time t being distorted at time t prime, you can look at the volume of this intrinsic coordinate system. And by having volume 1 at time t and some other volume at some time t prime, you can describe density changes. So in our argument so far, we include density changes. Now it doesn't require any additional mathematical treatment. It's when describing a strain with the deformation gradient f, and then with eliminating the rotation going to the Cauchy tensor, and all those steps, we allow density changes. It's not restricted to material of constant density. So far, I only looked at two states, describing a strain between a state t prime and t. But a continuously flowing material will undergo a sequence of strains. So let's look at least the first approximation of flow and include a third state. Let's say we go from t prime to some intermediate state t double prime and to the final state t. Our material vector will go from its length and direction at the prime state here. This is a prime, go to a double prime to a. This line is the path of the material point P, which is attached to one end of our material vector. We're talking about two strains, F1 here, this would be the first strain, and then F2 as a sequence in that situation. Now, sequential strains occur quite often in processing applications. I see you looking for that figure. I'm not sure whether, but it's the same old figure, which I think it's somewhere. Yes, okay, in page 10 you found it. Okay, good. For instance, in fiber spinning, you have flow inside the die, that's shear flow, and then you have stretching outside the die. So you have a sequence of two types of flows, and you could describe, say, the shear flow in this first part and the stretching in the second part, something like this. So it's quite realistic to use that approximation. The residence time of our material here is given as t minus t prime, and the position change between x and x prime is given just by an integral over the velocity during that time interval. The infinitesimal material vector, which we denoted A here, this vector at point P undergoes the first strain here from t prime to t double prime, and that strain is described, we assume that we know F1. It's fully described by F1. So we have the relation defined. And then the second strain between A double prime and A prime is given again by a defined strain. We call this F2. But we are interested in the total strain between T prime and T. So we are going to combine this information. We put A double prime up here into this expression. So we replace this by A times F2. So you see this relation A prime now is equal to A times F2 times F1. And the total strain is given as the product of F2 times F1. Now, that's interesting in several respects. One point is that the strain is not additive. Wouldn't you have guessed? I would have guessed that we would just add up those strains. You know, we deform it a little bit, and then we deform it more, and then the total strain is an addition of the two. But you can see that the strain is given as a product of those two deformation gradients. Secondly, note that the sequence is reversed. We have F2 times F1. So we're kind of going backwards in the strains when formulating this product. We can introduce that into the Cauchy strain tensor, which is defined as F dot F transpose, and do all the manipulations which you see here. The transpose here, again, is performed by changing the order of those two terms and making each of them transpose. So we have F2 times a term which is F1 times F1 transpose. This is actually the Cauchy tensor of the first strain in our sequence, multiplied with F2 transpose. So the result here, the total strain, Cauchy strain is given by the Cauchy strain of the first deformation with a product from two sides coming in with the deformation gradient. So it's quite complicated. You have to be careful with those manipulations. And certainly, I just want to stress this on the bottom, the Cauchy tensor is not the product of C1 and C2. It's a more complicated arrangement. If we go to shear flow, use a simple example, we know the result already. We know that a shear strain going from T prime to T double prime would be given by just a gamma, here integrating gamma dot over that time. I didn't draw this. That's too simple here. Just look at this. We're adding those two strains. The total shear is just the integral of gamma dot from T prime to T, or it's just gamma 1 plus gamma 2. That's the total strain. And if you put this total strain into the finger strain tensor, we replace gamma square with gamma 1 plus gamma 2, and this will be squared. And here is also the sum of those two. So the problem will really arise in the square terms. And since there's a 1, you cannot just simply add things. But you could go through the manipulations which I did before in general terms, and then you could derive this relation yourself. That would be a very nice test to do at home. This is the, we have to break to switch the tape. There's also the first homework set. I don't know, has it come around? So I just formulated a few typical problems and marked 3 of them for your exercise, for your enjoyment. Chemical Engineering 757, Polymer Rheology Lecture 3B. We are also interested in the rate of strain, not only in the strain, but we would like to define the rate of deformation quantitatively. And we will use the strain as it was defined before and just take the time derivative. But time derivatives are quite tricky and they can be quite exciting. So let's start very simply. And I have a sheet here where I want to describe the time derivative of a finger strain tensor. Of the deformation gradient tensor, f to the minus 1. So that's what we would like to calculate, the rate at which the deformation gradient changes. And ddt is simply a time derivative locally. And the f to the minus 1, the inverse of the deformation gradient, is defined as the derivative of r, any small vector r at time t, with respect to r at time t prime. Remember, in defining a motion, we looked at two states, say t prime t and t, and a small displacement at time t is represented as a small displacement at time t prime. And those little displacements, that's what we are talking about. This is an incremental material vector we are discussing. So this is r and r prime. And the time derivative of this now can be expressed, as such, we interchange order. And we have d dr prime of the rate of change of r. And we could express this as r dot. This is the next quantity. So we have d dr prime of r dot. And we can rearrange that and can express that in terms of here the finger strain tensor and not the finger strain, the inverse of the deformation gradient and delta u. Now, how do we replace this term here, ddr of r dot? How do we rewrite this? R dot is really the rate at which points A and B move apart. Here, A and B are connected by the incremental vector r at some initial time. Now, A is moving at some velocity ua, and B is moving at the velocity ua plus the increment which is due to a velocity gradient. See, the velocity is different when you move away from A, and this change is given by the local gradient, delta u, and this is being multiplied with r, and so this is the amount at which the velocity of B is larger than the velocity of A. So the velocity, or the speed at which those two move apart, is given as r dot delta u, and this is given as this expression here. This is r dot. In r dot, we put into our expression here. This is the expression up here. This is, we're moving this in here, and then we take this entire expression and move it up here to get the final result. Now, this expression, now when putting this r dot in here, is ddr of r times the velocity gradient, and the velocity gradient is constant in the vicinity of this material point A. And it is constant because we're talking about an infinitesimal material element. Everything is linear in that immediate neighborhood of point A. So delta u is constant, and this derivative is simply 1. So this the second expression up here can be replaced by delta u, and we simply have the time derivative of f to the minus 1 here, which we might denote as a dot here, and put on top f to the minus 1 dot, and that's equal to f times the velocity gradient. f to the minus 1. And you can do this with all types of strain tensors, and it will always be the same manipulation. You can do this with the finger strain tensor itself, or we use the inverse of the deformation gradient. That's what we just calculated, the time derivative of this. And we would say the time derivative of the finger strain tensor is given as the time derivative of this product. We differentiate in parts. Take the differential of the first part, multiply with the second, and then take a differential of the second, multiply with the first, and then we replace each of those time derivative with the result which we just had before. That's where the velocity gradient comes in. So this is the result we had for the first term. And here, delta u comes in again because of this time derivative. That's what we had calculated. So the time derivative of the Cauchy strain tensor is given by the strain tensor itself, but dotted in from the outside with here the transpose of the velocity gradient and the velocity gradient itself. And that's, at least it's an interesting formulation. It's the time derivative of the strain tensor is connected basically with the strain itself and with the velocity gradient at which the strain is occurring. The strain and the magnet, or the rate at which this process is coming in. There's a simple case where we can calculate the components. We could, for instance, take the components of a strain tensor, Cauchy strain tensor, or finger strain tensor, in shear. Now, the shear strain, gamma, is given as an integral over the shear rate from t prime to t. And if we take a time derivative of this function, then all terms drop out. There's no term appearing with t in it except for the upper limit. And if you remember the Leibniz rule for taking this derivative, it's equal to the derivative of the upper limit, which is equal to 1 in this case, multiplied with the kernel function at the upper limit, which is gamma dot at time t, and that's the result. So the time derivative of gamma is just gamma dot t, and that's what we knew from the beginning, I guess. That's what we would have expected. Now, let's apply this to the Cauchy tensor. We take the time derivative of the Cauchy tensor by taking the time derivative of each individual term in that matrix. The time derivative of gamma is just gamma dot, and the time derivative of gamma squared is gamma 2 gamma gamma dot. Right? And gamma is again given by this integral up here. And you can do the same thing with the finger strain tensor. Now, you could also take the Cauchy tensor and multiply it, as described before, with the velocity gradient, and then you should get the same results. So that's another test which gets you used in manipulating those results. There are fluids for which the past strain is completely unimportant as much as the stress concerned. And those fluids are called Newtonian liquids, Newtonian fluids. Newtonian fluid, the stress in a Newtonian fluid is given by the instantaneous rate of deformation independent of any past history. So we would like to define now the rate of strain tensor not at some past time, but at time t, at the current instant. And we can do that by taking the rate of strain tensor, here the finger strain tensor, and introducing the limit t prime going to t, or we take the Cauchy tensor, t prime going to t, and the limit is equal to 2d. Let me show you how this works. We derived this before here for the finger strain tensor, for instance. This is the finger strain tensor. Now, if we take the limit for this expression for t prime going to t, then the strain is not existent. There's no deformation occurring. During that increment of time, the shape is constant. That means that the Cauchy, or that the finger strain tensor is reducing to a unit matrix. Remember the components of the Cauchy tensor and finger tensor. Maybe if I go even back further, have some typical. Here is a typical finger strain tensor and shear. You have those diagonal terms, and if the strain is equal to 0, because t prime is approaching t, then you just have 1s on the diagonal. Okay? So this will be reduced to 1, this will reduce to 1, and then the rate of deformation reduces to just the velocity gradient transpose plus the velocity gradient, and that is the definition of 2 times the deformation, 2 times the rate of deformation tensor. So by going all those complicated steps describing large deformations and taking the time derivative to describe rate of deformation, we come back in the limit to the well-known expression of the rate of deformation tensor, which is used in Newtonian liquids for describing the stress. This limit to vanishing, this limit of t prime to t, or eliminating the strain history, not accounting for that, is also interesting for very slow flows where the material is relaxing all the time. So any past history is forgotten already, so it's not very important. Or it's interesting for materials which are only slightly elastic, so their memory is very, very short, materials which are very short relaxation time. And in those cases, one could actually expand the strain tensor in terms of a Taylor-type series, taking it equal to 1 at 0 strain, and this rate of deformation times time, and just linearizing this. And this can be used in some simple expression. It's quite handy. Okay, now so far I just talked about the strain and its derivatives. And now let's take the derivative of an arbitrary tensor t. And this could be the time derivative of a stress tensor, for instance. And we will do this in several different ways. Let's do it the conventional way. The derivative of the tensor t with respect to time is finite in a non-steady situation. If the stress, say, if you're looking at the material at one position, and if the stress changes at that position in time, then you have a partial derivative, and you have a finite quantity here. This contribution is the so-called substantial derivative, and it also contains the contribution when you move from one position with the flow, with the velocity, local velocity, to another position, and the stress is different at this other position. Then your material element will undergo a stress change from the first position to the second, and there will be a time change of stress because of that motion. And you don't have to look at stress. You can look at the concentration of some material in a second material and follow that concentration and calculate those time derivatives. But here we are not looking at scalar properties. We are looking at material lines, for instance, and material planes in space. And we want to describe those, and we want to take time derivative of those. We take time derivatives of vectors and so on. So how do we do this? We can do this in most interesting by moving with the material, and this would be a Lagrangian approach. But we can do even more, and we need the blackboard for that. We are moving with the material. So we have some material which is at different shapes at different times. And now we can use an observer which is moving with the material like this, and it's not changing. It would be, this should be an orthonormal coordinate system which is translating but not doing anything else. That's the so-called Lagrangian approach. Now you can choose a coordinate system which locally rotates with the vorticity. The vorticity at point P in this moving material element. And as this coordinate system is rotating, you are introducing a contribution to your observation, to your contribution to your time derivative here, just due to the rotation of that coordinate system. Now, that's not very popular. It was popular for a while to do that, to use a co-rotational coordinate system, but that has not, it's somewhat unphysical. Doesn't give interesting constitutive equation, it seems. But you could choose a coordinate system, as we did, for describing the stress, which is co-deformational. You could use a coordinate system which is of unit length at time t, like Lodge was doing for describing his Cauchy tensor components. And you would have then E prime, E here, and you would have E at time t, and this would be would coincide with the coordinate system you're looking at. You're using macroscopically. This would be delta. Okay? So now you have a coordinate system in which you describe your material points, the state of the material. And this coordinate system is deforming as the material moves on. Now assume you describe a line which doesn't change, maybe a line which is just constant like this, moving along here, and your coordinate system is changing. Then the time derivative you are expressing that coordinate system is finite. Your object is not changing, but your frame of reference is changing during the deformation. And if you do that in a co-deformational coordinate system like I described here, then you get a term here in the back where A is equal to +1. There are many different ways of doing it. If you do it in a system, coordinate system, which is just rotating with a local vorticity, you get A equals 0. And if you do it in a contravariant base, then you get another type of time derivative. Let me describe the other base, which could be used. Instead of using this type of base, we could say we have, vector E1 prime here and vector E2 prime, and those two material vectors are describing an infinitesimal plane in our deforming material system. And planes are described by vectors normal to those planes, and this would be called E3, and Lodge uses a superscript for that, and E3 is equal to E1 cross E2, and we do this in the prime state. If you do this in the T state, you have an orthonormal system, and it doesn't give anything interesting. If you multiply in this orthonormal system E1 times E2, you get E3, right? So this coordinate system, if you define now 3 of those, not just one, you have, say, E3 defined like this, and then you have another one, I'm using this, E2, and wherever E3 is in the prime state, you're using those 3 vectors as your base for describing the deformation. Note that E1 and E2 are material vectors. The material points in the plane they are in are remaining in that plane. So this is really a material plane. But as this plane is moving around, this is a pointer which is moving around, describing the plane. So this is not a material vector anymore. I won't go into further details. I hope you got the flavor of working with those coordinate systems, the different choices. But you can use that as your base. It's also a co-deforming material system, but it's depending on the deformation of the planes. And you can calculate time derivatives. And again, if those planes are changing, you might look at an object which doesn't change at all. You still get a finite time derivative. And this. Yeah?
You also rotate with the local vorticity, right?
Yes.
This is the first.
The co-rotational base, the question is what's the difference between the contravariant, this is the contravariant base, and the co-rotational base. Now, the co-rotational base is always orthonormal, and it's like a little propeller. Assume you have a deforming material, and in this material you have your base, which is always at right angles and of unit length, spinning around at local vorticity. And it gives quite arbitrary results. That's a good point. Those are not material lines. Yeah. And they are just defined with a local vorticity. I use the symbol W here describing the local vorticity. So if you have a velocity field which gives rise to velocity gradient, then you can calculate the vorticity and you get this type of expression. Okay? There are long textbooks, I think, in Showalter and also in Bird, Armstrong, and Hassager, where they describe those time derivatives very successfully. Now, after all this, let's see whether we can describe a complicated flow. And you might remember that in the beginning, I talked about a complicated flow of a material element moving into a contraction, something like this little element. And we would like to describe the stress of this material element. And the first step in our approach now, after having talked so much about strain tensor, the first step would be to describe the strain and also describe the strain history in this case. Let's assume we know the velocity field and we can track this material element along its path. And the question is, how would we describe its strain? How would we describe its strain history also? The result of all this, if we go through all the motion, will be something like this. The strain tensor is given as by the stretching of this material element. There's some stretching involved. And there will be some angle changes. There will be some shearing of this material element. And all of this has to be accounted for in our mathematical formulation of that strain. Also, there is a rotation. This element moves on a curved streamline, and we have to account for the rotation of this material element. See, it might be stretched in one direction first, and then it's rotated, and then if we keep stretching in that same direction, this element doesn't experience stretching in one direction. As it rotates, it's being stretched sideways for a while. So somehow we have to include the rotation of the material element in that whole picture. And that's why we would take the local angle of the streamlines here. Here, the local angle of the slope of those streamlines here is quite important, and we have to introduce a rotation after having calculated a Cauchy strain tensor on a tilted element. Putting in with Lodge's approach, putting in the material coordinate system. and then transforming everything to a regular coordinate system. Now, for doing that, let's see whether I can do this in 2 minutes. We would look at axisymmetric flow. It's given like this. A material element is moving on stream surface, which are really axisymmetric here. And at time t prime, it is somewhere here. And at time t, it is forming an orthonormal system. And we can pick any convenient material vectors for describing that strain. Now, one convenient material vector is the tangent to the streamline. That would be E1. And that consists of material points which always will be tangent to that line. So in a previous time, we know it's tangent to the stream surface. So we already know the direction at 2 times of this material vector. That's quite convenient. And the stretching is really given by the acceleration from here to here. And I give you all the equation. Now, in circumferential direction coming out of this, note that this element really belongs to a ring. It's an axisymmetric flow, and this is a hoop element going all around. And if this ring goes to a radial position which is bigger, then all the elements in 3 direction will be stretched in hoop direction. So we have a larger deformation there. Okay? See, don't know whether I'm allowed to speak a little longer here to finish this up would be very nice. So the kinematics we say is given. This is the velocity field. Streamlines are defined here with the velocity field. Residence times we get by integrating the velocity along the streamline. And shear rates we get by looking at the streamline and moving away from the stream surface by the gradient of the velocity. So those shear rates are accessible. We would take a material element now, which is orthonormal at time t, and at a previous time it will be somewhat flatter because there's some extension involved and it has been exposed to some angle. The stretches here in 1 direction and in 3 direction, that's what we just talked about. That's done very easily. The material vector in 2 direction, this material vector here, that's quite complicated because there's a thickness change and there's an angle change. And that can be accommodated here. This is the thickness change, and then there's an angle change with a shearing, and the total results in a deformation gradient tensor. Same thing as we did before, but it's just a more complicated flow, deformation gradient. And with that deformation gradient, I come back to the first picture. We calculate the Cauchy tensor here. And then we rotate the Cauchy tensor from the tilted, from a slope into the global coordinate system. And that's why we need those rotation matrices. And those actually have the same property as we had before with R. Q multiplied with Q transpose is equal to a unit matrix. And you can check that with down here. Okay, this brings our this description of strains to a conclusion, starting out with a simple picture of stretching lines and changing angle between lines, then formulating that concept quantitatively for shear flow and extensional flow, taking the time derivative to look at rate of deformations, and then applying this to a complicated flow situation at the end, where we really use exactly the same approach by picking 3 material vectors in a complicated flow and then calculating the finger strain tensor basically from first principles. Next time we will talk about the stress, and then we put everything together into a constitutive equation.